All right, welcome in Calc 3. It's Thursday, August 26th at the end of week 2. And today we're going to finish up 11.3, which is talking about dot product. I'm going to do another projection problem, and then we're going to talk about work, and that is the physics aspect of the word work. Yeah, so we're going to talk about that because that's naturally what a dot product does. And then we're going to move into 11.4 and learn another type of multiplication. This time it's going to take two vectors and multiply them together to get another vector. And this is a different type of multiplication that works really nicely and has its own uses. And so just like we learned the cross product and the dot product and its uses, we are then going to work on the cross product and figure out its uses and what it can be used for and calculated with and all sorts of good stuff. So let's get started. I'm going to continue on with a word problem here with that's going to use projections in a very natural way, just to sort of remind ourselves of projections again. And here we go. Last time we learned how to project one vector. Let me make sure the letters are the same. I want to project U onto V. Okay, and to do so, we came up with a formula. And that formula was u dot v divided by v dot v times the vector v. And this makes sense, right? Because this is a scalar. This is a scalar divided by a scalar. So this is a scale of v. And remember, the projection vector of u onto v needs to be parallel with v. And so it has to be a multiple of v. What is that multiple? That multiple is u dot v over v dot v. Another way that the book actually writes this is they don't think of it as the dot product in both. They think of this as the magnitude of v squared. These are equivalent. Either way you want to think of that formula works for me, right? Picture time again. So here's v, and let's say this is u, right? And what I want to do is project this down into a vector parallel with v. And so this right here would be the projection vector of u onto v. And why is this really useful? Well, let's revisit that inclined plane problem that we were talking about last time. And so let's see, here we go. We have an incline, let's say here, and I have a 600-pound boat, and it sits on this ramp inclined at 30 degrees. Okay, so here's another awful picture of a boat coming up. Okay, and it's being, let's see, I'm just literally copying this, and I still can't draw a boat. Wow, okay, cool. Pretend that's a boat, and it's being like anchored or connected to something off screen like that, right? I think that's personally the worst drawing I've ever made, but that's okay. That's cool. Anyway, we got a 600-pound boat. Okay. And the ramp is 30 degrees. And my intuition says this is going to want to roll down the ramp, right? Obviously. Yeah, it's going to want to roll down the ramp if this was not connected, right? So what sort of force do I have to provide so it doesn't roll down the ramp, right? So what force do I have to give this? What is required to keep the boat from rolling down the ramp? So I would like to provide some sort of force in this way, right? This way, to keep it from rolling that way, right? Now, it's nice to draw a little picture here of what's going on. 600 pounds, well, that's the weight of the object, and the weight of the object acts downward, right? So that's a force, and it's a force acting in the downward direction. So what I could do here is model that by just drawing a vector straight down to represent the weight of this object. Let's call that capital F. Right? So capital F, the magnitude of capital F is going to be 600 pounds acting in the downward direction, right? But what I'd like to do is not all of the force is acting in the direction of the ramp. So do you see, I'm going to need to project this force onto the direction of the ramp to see how much of this weight is actually acting in this direction and how much is acting in the orthogonal against the ramp this way direction. In other words, I need to find that right triangle thing going on here, right? So if I was to think of this ramp as a line like this, I can notice that I have this right triangle forming here, right? Like here. In other words, think of the projection of F onto, well, the ramp, okay? And that's going to be this vector here pointed to here. That's the force that I need to counteract. We called that W1. We called that the projection vector. So all I have to do here is find out, I need to get a vector to project onto. And once I have that vector that I can project onto, I need to actually then do the projection, right? And that'll give me what sort of force I need to work in on that way, right? So to get the vector that I want to project onto, I'm going to utilize the fact that I know the ramp is at 30 degrees. So I could say that vector v, let's make vector v a unit vector pointing in the direction of 30 degrees. So that would just be going back to our first chapter this semester, first section. I could just say that v is cosine 30 degrees I plus sine of 30 degrees j. And would you agree that that's a vector now pointing in the direction up the ramp, right? And so that will now be what I want to project the force onto. I want to project the force onto a vector to get what component of this force is acting in parallel to the ramp. Nice. So that means now all I have to do is construct W1, which is going to be the projection vector of F onto V. So now using that formula, I'm going to say that this is F dotted with V divided by V dot V, and then multiplied with V. So it looks like I got some things to calculate here, right? First things first, V is a unit vector, right? Because of the way I formed it. Remember, cosine, if I did this, the magnitude of this would be the square root of cosine squared 30 plus sine squared 30. And cosine squared 30 plus sine squared 30 is 1. So V dot V is the magnitude of V squared, which is 1. So this ends up just being F dot V times V. So all I have to do is dot the force vector with V. Okay, to get that accomplished, I now have to write F in terms of its components, right? So what is F? Well, F is a vector acting straight down. So it's all J component, isn't it? And in fact, it acts downward by 600 pounds, right? So F I can think of is negative 600J, acting in the down direction like that. And V I can think of as, well, it's cosine of 30 degrees, which is root 3 over 2, I, plus the sine of 30 degrees, sine of 30 is 1/2. And so there's V. Now all I have to do is dot those together. So F dot V is going to end up being, the I component here is 0, so 0 times root 3 over 2, plus negative 600 times 1/2 J. Nope, not J, sorry. It's just the components, right? It's the dot product. So number times number plus number times number. So this dot product here is going to be negative 300. That's the dot product of those two. And now all I have to do is multiply V by that. So what is the force required to counter this? I need the force acting like this, negative 300 times V. In other words, that would be negative 300 times the vector root 3 over 2 comma 1/2, just like that. Yeah. And I could multiply that through or whatever, keep it like that. That would be the vector. That's the force vector that I need to counter. I can tell you the magnitude of it, right? The magnitude of this force, since this is going to be a unit vector, V is a unit vector. So this means that the magnitude of the force is 300. So I would have to apply a force of 300 pounds to keep this from rolling down this 30-degree incline. Okay? So magnitude of W1 is equal to 300 pounds. Okay? And so therefore, that is what I would have to apply to keep this from slipping down the ramp. Awesome. All right, one last application that we're going to do for dot product, and that is the idea of work. All right, so in physics, you might have come up with the definition for work. You talk about work in Calc 2 a little bit. If you take Calc 2 at Rock Valley, you get to talk about work a little bit. I think we talk about work even in Calc 1 a little bit. Anyway, the work done by a constant force along a line of motion is F times the distance, right? So work equals a force times distance, yeah? Now, the problems up to now have basically been the forces acting in the direction of the motion of the object, right? So in other words, here's a box, and I apply a force to it, yeah? And it moves in this direction as well, right? And so the force that I apply is actually working exactly in the same direction as the displacement is, right? Or as the distance vector, in what direction I'm going there, yeah? That those are the same direction, those are parallel, right? But what happens if it's not, right? So for instance, if I'm trying to drag something here, like if I'm trying to drag this box, right? And I'm taller than the box, so I want to attach something here, and I want to attach a rope, and I want to drag it this way. So I'm applying a force actually this way. And as you know from physical sort of intuition, we know that most likely the box is not going to fly that way, right? It's just, you know, even though I'm pulling on a rope this way, it's not likely that this is going to just want to fly up like that in the same direction, right? It's likely, since this is maybe heavy, that it's going to stay on the ground. And it's actually just still going to move this way, right? Still going to move this way, even though the force is being applied in this way, right? So it looks like the work done, if I want to find the work done, is I now have to figure out how much of the force is acting in the direction of motion, right? Some of this is wasted in this direction, right? Some of this is being counteracted by the weight of the object acting downward. But some of this force, even though it's acting this way, some of it's contributing to keeping it, you know, the weight is keeping it down, and some of it's going towards moving this thing forward. And the work is exactly that much force that's acting in the direction of motion, right? So I want to figure out how much that is, yeah? So would you agree that the work here, the force acting in the direction here, let's give this a name. Okay, they say PQ, all right. Yeah, that's probably true, because this is like starting at point P and then it's being moved to point Q, like that. And so vector PQ is my distance, yeah? So they say that the work done by this force, how much force is acting in this direction? Well, that is going to be the projection, right? In fact, the force is the projection of the force vector onto the direction vector, right? It's only this much that's acting that way, right? And that takes care of the force part. Now I just have to tell you about the distance part. Well, how far is this going? Well, how far it went is however long this vector is. So that's going to be the magnitude of PQ. See that? And so the work done by this force, even though it's not acting in the direction of motion, this work is still this formula here, right? Now, let's get into another way of thinking about this. Using one of our formulas from before, and I don't know if I have my notes here. One of our notes from the projection formula last time said that this is really just the magnitude of the force times the cosine of the angle between it. And that should make sense, right? Because notice this is the adjacent side of this right triangle. Guess I didn't need my notes. I could just show you again, right? So if this is the angle that it makes here, right? This is parallel to PQ, yeah? And this is the adjacent side of this triangle. And so another way to think about the length of this, right, is that it's going to be the magnitude of F times the cosine of theta. But now, wait a minute. Look at this. Isn't this just the magnitude of F times the magnitude of PQ times the cosine of theta? And where have we seen that formula before? This is the alternative formula for the dot product. Said another way, this is as simple as finding f dot pq. And so there we have a really nice direct application of what the number is that you get for the dot product. If one of your vectors represents a force and the other represents a distance, then dotting those two together will get you the amount of work done by that force on that object, right? Just directly. And so yet another reason why the dot product is defined the way it is. Yeah? Awesome. That finishes 11.3. Yeah? Any other questions with that? Are we doing all right with this? Because we're going to now move on to 11.4 and talk a little bit about cross product. Awesome. Okay. All right. So vectors have all sorts of different operations you can perform. And we're ending up going to have two major ways of multiplying two vectors together. The dot product takes vector times vector and gives you a scalar. The cross product is going to take vector times vector and get you a vector. Yeah? And so sometimes it's called the cross product. Other times it's called the vector product. Some books will use that phrase as well. Okay. Now, I'm not going to actually write a definition at first for this because I do not want you memorizing the direct definition. The best way to remember and to recall the cross product is actually some sort of matrix visual way, right? If I just write down the definition, it's going to look like just a lot of random letters everywhere, and no one thinks about it in that way, right? Here's how we do think about it, though. We think about it like this. U cross V, okay, is going to equal this 3 by 3 determinant. Now, I'm going to have to talk about what a 3 by 3 determinant is. But the first row, you put I, J, and K. The second row, you put the components of U. The first, or I should say the first vector, which happens to be U. So the components of U go there, and the components of the second vector go here. Okay? So I'd like you to remember that. That is a nice compact way of remembering how the cross product will go. Now, I'm going to show you, or either remind you or teach you, how to unpack that. What does that calculation mean when I see that? Okay? So now I'm going to do a little side quest here where I start talking about determinants and how to calculate it. That's what we call this. This is a 3 by 3 determinant. 3 rows, 3 columns, 3 by 3 determinant. Okay? Before we can do a 3 by 3 determinant, though, you need to know how to do a 2 by 2 determinant because that's part of the calculation. So again, let's do a little side quest here to talk about how to calculate things that look like this. For example, if I have a 2 by 2 determinant, by definition, this is all this means. So go ahead and put like a 2 there, a 4 there, a 3 and a -1 there. And I ask you to calculate the determinant of this matrix. Okay. All this means is you do a cross multiplication. You're going to do 2 times -1, 2 times -1, built-in subtraction, then you do 3 times 4. Okay? So I'm going to get -2 minus 12 or -14. So I would say that the 2 by 2 determinant of this 2 by 2 matrix, 2, 4, 3, -1, is the number -14. Okay? All right. So in general, if I have A, B, C, D, like that, the 2 by 2 determinant of this is just A times D, built-in minus sign, C times B. Okay? So 2 by 2 is real easy. It's just that visual sort of multiplication, right? So for instance, if I had 4, 0, -6, 3, I would end up with 4 times 3, which is 12, minus 0. Negative 6 times 0. So I get 12. Okay. Now, since 2 by 2 is really easy, that's cool and all, let's get on to how do I do a 3 by 3, right? Well, a 3 by 3, you have to break it down into 3 2 by 2s, right? So the determinant calculation becomes a little bit more complicated with each dimension that we layer on, right? So a 3 by 3 determinant ends up calculating 3 2 by 2s in a certain way. So let me show you what I got going on here. Suppose I want to figure out 1, 2, 3. Let's do 4, 0, 1, negative 6, 3, and 2. Okay? And I wanted to calculate this 3 by 3 determinant. Here's how we'll do this in this class. There's many ways to do this. And to figure out what a determinant actually is and how it works and why it works the way it does, you have to take a class called linear algebra, which is something you can take after Calc 3 and concurrently with differential equations. All right, so this sort of math is talked a lot about in linear algebra. So for Calc 3, I'm just sort of telling you this is the calculation, and it's a real nice way of remembering instead of having to memorize a whole bunch of random letters. But there is more to the determinant and other applications that we're not getting into here. But you might be interested in that. So you can either look that up or take a class called linear algebra. Yeah. So now, let me get through here. Here's how I do this. We expand along the first row, it's called. And so here's what you end up doing. Take the first thing in the first row and write it down. You get 1. Now you're going to multiply that by a 2 by 2. What 2 by 2? You hide the column that 1 is in, and you hide the row that 1 is in. You see that? And so you get this bottom right 2 by 2. That's the 2 by 2 that you're going to multiply 1 by. So I'm going to multiply by the 2 by 2, 0, 1, 3, 2. Okay. Now here's where the number one mistake happens all the time. There's a built-in minus sign right here. Then you put the number, the second number, so whatever that is. So built-in minus sign, 2. Times what 2 by 2? Hide the column 2 is in, hide the row that 2 is in, the top row, and whatever the 2 by 2 you're left with, that's what we got. That's going to be 4, 1, negative 6, 2. Okay. Then plus 3 times what 2 by 2? Hide the column 3 is in there, and I get 4, 0, negative 6, 3. Okay. Now go ahead and just do those 3 2 by 2s. So I get 1 times 0 times 2 minus 3 times 1. Minus 2 times 8, 4 times 2, minus a minus 6. Plus 3, 4 times 3 is 12, minus 0 times negative 6, which is 0. And I go ahead and I just calculate that arithmetic, right? So let's see what I get. I'm going to get negative 3 here. I'm going to get 8 plus 6, which is 14. 14 times 2 is 28, yeah? Right? 38. No, 14 times, yeah, 28. Minus 28. Yeah. Plus 3 times 12, 36. I think I did some arithmetic there, all right? Did anybody else get 5? After doing that? Minus 3 minus 28, negative 33, negative, oh, wait. Negative 33 plus 36, I got 3. Ooh, arithmetic is hard, yo. I'm going to ask if anybody can confirm that's watching live. I don't know. Did anybody else get 3? Oh, no, I was right before. Negative 28 minus 3, negative 31. 36 minus 31. I was right the first time. 5. Oh boy. Oh boy, I need more coffee. And I got nobody in chat here, so I don't know if I've confused utterly everyone now. Anybody else get 5?
Yeah, I had to pull out the calculator.
Yeah. So, yeah, I should have, right? Stop this doing it in my head business. All right. So let's kind of review those steps real quick, and then we're going to apply it to this 3 by 3. Now, this 3 by 3, the first row aren't numbers. They're not numbers. They're vectors. They're I, J, and K. But that doesn't really change the calculation much. It's just that the result of doing this cross product is going to end up being a vector instead of just a plain old number, which is what I got here, right? Because these are all numbers. Yeah? And so, again, we're going to always expand on the first row. So 1, whatever's here, times the 2 by 2 there. Built-in minus whatever's here, times this 2 by 2, plus whatever's here, times this 2 by 2, and then do those 2 by 2s and get our result. We're not going to be able to combine, though, for a vector because you can't combine I, J, and K. So now let's go ahead and do a cross product calculation here. All right, so here we go. Suppose I have example. Suppose I have u, which equals I minus 2j plus k. And I have v, which equals 3i plus j minus 2k. Okay. And just for calculation purposes, I want to calculate u cross v. We'll get into what u cross v actually means and what it does and all that very soon. But for right now, let's just see if we can just flat out just calculate it. ijk goes on the top row. U goes on the second row, so I'm going to put 1, negative 2, 1. And then v goes in the next row, so 3, 1, negative 2. Okay. Now I follow the same pattern as I did before. So expand on the first row. So I'm going to have I times the 2 by 2. This is probably the last time I'm going to write the 2 by 2 out because I usually do that in my head. All right, so but it's I times this 2 by 2. Built-in minus j times what 2 by 2? We're going to get 1, 1, 3, negative 2 plus k, 1, negative 2, 3, 1. And now I just complete this by doing those 2 by 2s. So I get, what is this? Negative 2 times negative 2, which is 4. 4 minus 1 times 1, which is 1. Negative 2 minus 3 times 1 plus k. 1 minus a minus 6. So you can see probably the number one mistake is just sign mistakes. Yeah, that's usually what happens with these. 4 minus 1 is 3. So I get 3i. Negative 2 minus 3 is negative 5, but it's negative 5 minus, so it's opposite, so plus 5j. 1 plus 6 is 7, so plus 7k. And there you have, if u and v are this, the cross product is that. Okay. And like I said, we're going to figure out what that does, what that means, why I care about that vector in particular. But are there any questions with the calculation here? Okay. Now, one thing we can talk about with cross product here is that it is a product, and usually multiplication is commutative. But I am going to calculate v cross u just to make sure. So let's actually switch this around. Okay. instead of u cross v, I'm going to calculate v cross u. And I'm going to actually do that calculation this way. All right. And so I go ahead and put v first. V is 3, 1, negative 2. 3, 1, negative 2. And u again is 1, negative 2, 1. 1, negative 2, 1. And I go ahead and I calculate my cross product again. And so here I'm just going to try to do this in my head. 1 minus 4. 1 minus 4. That's negative 3. Minus j. J is going to be 3 times 1, so 3 minus a minus 2. 3 plus 2, so I get 5. And then plus k. K is the 2 by 2 there is going to be negative 6 minus 1. Negative 6 minus 1 is negative 7. So I get the end result of negative 3i minus 5j minus 7k. And so the first thing I notice here when I do this, I did not get the same vector. So it's not true that u cross v equals v cross u. Uh-oh. So this is a multiplication that is not commutative. You can't swap the order. You don't get the same thing. So order matters in a cross product. Now, with that being said, is it just as easy as this was all, plus, 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 and this was the opposite, negative, negative, negative? And that, I can tell you, is true. So yes, they're not commutative, but they are, when you do switch, it's predictable what's going to happen. And in fact, this doesn't prove it. This is just one example. But we can prove, either in a little bit, or you can prove on your own, that u cross v is equal to the opposite of v cross u. That is a thing that happens. That is a rule, and that will always be the relationship. We'll see visually why that's true, if nothing else, later. Okay, but please remember, you can't do that with one example. I mean, just one example did that. That's not enough proof. But I'm going to sort of do a spoiler alert for something that we're going to see later, why that's true. Okay, so big idea here. Cross product is not commutative, but it is predictable. Right? It is predictable. Okay. Let's do another one. I'm going to take v and cross it with itself. Okay. So what would v cross v be? Well, okay. V crossed with v. I, j, k. V is 3, 1, negative 2 again. And so is v, 3, 1, negative 2. And I go ahead and I do the I. Think about the 2 by 2 here. So it's going to be negative 2 minus a minus 2. So negative 2 plus 2. Negative 2 plus 2 is 0. Minus a j. J, which is 3 times negative 2. So negative 6 minus a minus 6. Negative 6 plus 6 is 0. Plus k. 3 times 1. So 3 minus 3. 3 minus 3 is 0. Huh. I get the 0 vector. V cross v, v crossed with itself, is the 0 vector. This is a rule. When I cross any vector, there's nothing special about the 3, 1, and the negative 2 here. Right? If this was A, B, and C, the A's and the B's and the C's would all wipe out and give me 0 in each one. So we have another generic algebraic rule. Crossing a vector with itself gets me the 0 vector, no matter what that vector is. Yeah? Interesting. So we got a couple rules already for cross product under our belt there, right? There's a few others. Let's bring this up. Oh, I don't think I got this ready. Nope. I have my stats book still up from the previous class. Hold on one second. Let me actually get the right textbook up here. All right, I think we're ready to go there. Yeah, take a look at this box of properties here. Yeah, oops, come on. There we go. And so here we have, okay, yep, that first rule right there is the one that we just said. It's not commutative, but it is predictable. Okay. Next one we got is that u crossed with the sum v plus w is the same as add u crossed u with v and u with w and then added those vectors. So in other words, cross product does distribute over addition, right? Okay, we also have scalar. If I scale the cross product of u and v, that's the same thing as had I scaled u and then crossed it with v, or scaled v and crossed it with u. Okay. Crossing u with 0 gets you the 0 vector. Crossing u with itself gets you the 0 vector. And then here's a really cool rule. This is how the two multiplications interact with one another. So if you take u and dot it with a cross product of v and w, it actually equals the u cross v dotted with w. This is such a funky rule. Look at this rule. It literally swaps the dot and the cross. Do you see this? u v w, u v w, and here it's dot cross, and here it's cross dot. That is ridiculous that it works out that nicely. That is such a cool pattern that works there. And this is actually quite useful for, for some applications, in the sense that it's really nice to be able to sometimes move the cross over here to maybe easier vectors or whatnot. And so then you're doing this dot product instead of this one. Yeah. So that's a really interesting rule, and that we don't use enough, but it's kind of cool. Yeah. Okay. Nice. Now let's see what we can do next. Let's get into some of the what does the cross product do, right? Why was it defined the way it was? What do I get out of that definition? Okay. So one of the biggest uses of a cross product is to generate vectors that generate a vector that is orthogonal to two vectors, right? So the first property that we need to really pay attention to the cross product is the following. When you calculate u cross v, you get a vector that's orthogonal to both u and v. Okay. Now I want to stop there and just talk a little bit of visualization with you. And notice that this is going to end up giving us the need that it has to be a three-dimensional idea, right? Because check this out, right? So suppose I have u, that's this, right? And now suppose I have v, like this, okay? And now I challenge you to draw a vector that's 90 degrees with u and 90 degrees with v at the same time. Now, obviously, you can do with just u, right? I mean, this vector here is 90 degrees, right? But if I pick that up and move it, that is not 90 degrees with v, right? So this is orthogonal to u, but not orthogonal to v, right? And if you try to do something orthogonal to v in this plane, in the two-dimensional plane here, and you try to move that, there's no way I can make a vector orthogonal to this vector and this vector at the same time. The only way I can make a vector that's orthogonal to both of these is if I'm allowed to use the outside of the paper. This pen sticking straight up would end up being a 90-degree angle with the vector v and vector u. Do you see that? And so the cross product necessarily is a three-dimensional idea. It's going to take two vectors which have to live in a plane, right? Pick up any two vectors, right? And they will, so I can say that they can live in a plane like that, right? And if I have that like this, now I have a cross product that's either going to go that way or that way, orthogonal to both of these vectors at the same time. Do you see that? And so that's nice. There's going to be need to find vectors that are orthogonal to two vectors at the same time. We're going to need that ability. And it's exactly the cross product that does that. It gives us a vector that's orthogonal to both u and v. Okay. Let's see here. Now, how do I know that? How do I know that that's true? Right? Well, I'll do one little argument that's true. Do we have a way to test whether two vectors are orthogonal to one another? We do, don't we? Isn't that the dot product? We did this last time. If the dot product of two vectors is 0, then they are orthogonal. So one way to demonstrate this, right, to show this, all you would have to do is calculate u cross v for any generic u and v, and then dot it with u. Okay, like that. Oops, I don't think I need a parentheses there. All right? See that? And what I would like to show is that this gets you 0. Right? Then I would take the same vector u cross v and dot it with v. And that better equals 0 when it's all said and done. Right? And you can go ahead and check that. All you have to do is just take a u, which is u1, u2, u3, and a v, which is v1, v2, v3. Go ahead and take their generic cross product, and then dot that vector with u, and you'll notice it all wipes out and gets you 0. Right? U cross v, same thing. Dot it with v, all crosses out, and gets you 0. All right? But that's how you would demonstrate that's true. Okay? All right. So now we know a little bit about what direction the cross product will go in, right? It's either going to be, so if I have these two vectors here, it's either going to be this way, right? Or coming out towards me this way, right? So it's either, that way or this way. That's the only two directions. It's not going like, this way with it or anything like that, yeah? So we now know a little bit about what direction the vector goes in, right? Now let's talk a little bit about how long, what's the magnitude of the cross product. This gets us to our second property. This says that the magnitude of u cross v actually has a little formula. And it's eerily similar to one that you know already. This is the magnitude of u times the magnitude of v times, would you believe it, the sine of theta. Come on now. Are you serious right now? Wait, wasn't the magnitude of u times the magnitude of v times the cosine of theta? Wasn't that u dot v? And you're telling me that the magnitude of u cross v is the same formula except with sine. And my answer is yes. That's exactly what I'm saying. So there's this really cool sort of, duality, analog, I don't know what you want to call it there. But yeah, there's that really neat, interesting pattern here. Now, to show this, right, to show this is true, to convince you that it's true, they go ahead and do a very straightforward proof, I would say. It does use a couple tricks, though, so I want to sort of go through that. They borrow the fact from the previous section that cosine of theta is u dot v divided by the magnitude of u times the magnitude of v. Right? So it follows that they're going to start with this, the magnitude of u times the magnitude of v times the sine of theta. Well, sine of theta can be replaced with the square root of 1 minus cosine squared theta. That's the Pythagorean identity, right? Sine squared plus cosine squared equals 1. And so any sine I see could be replaced with 1 minus cosine squared, the square root of that. And this is nice to work with because I have a formula for cosine of theta. Cosine of theta is this, so they plug it in for that. Now they do a little bit of arithmetic or algebra that they don't show you. They're getting a common denominator, and then they're taking the square root, and it actually gets into this looking right here. Okay? Then they go ahead and multiply that out. It's messy. They did not show you all the steps. This is a lot messier. They multiply this and factor that actually. And this actually comes out to be that squared. They rearrange it, and that, lo and behold, that combination of letters is U cross V. U cross V. By the way, their definition of U cross V, they told you it's this. I showed you just this, right? But if you actually go ahead and write this out, you actually get this, right? And that's their definition of the cross product. And that's why I don't have you memorize that. That's silly to memorize. I mean, how would you memorize U2V3 minus U3V2 minus U1V3 minus U3V1 plus U1V2? It's a lot, right? A lot of detail to memorize. There's a pattern to it, and you certainly could, but I hope you agree that a lot of people think of it this way. It just organizes the work a bit better, yeah? Okay, very cool. So, with that being said, we get that first result. We get that the magnitude of U cross V is equal to the magnitude of U times the magnitude of V times sine of theta, and it's a little bit of a trig trick, right? It's a little bit of a trig trick, and so that's how they end up getting that, okay? Now, 3. If I happen to have two vectors whose cross product is 0, okay? This happens if and only if okay, U and V are scalar multiples of each other. Wait a minute, didn't we have a nice shortcut way of saying that? Isn't that saying that U and V are parallel? In other words, i.e., U and V are parallel. Huh. Okay. So wait a minute. Let's recap. You're telling me that U dot V being 0 tells me that two vectors are orthogonal. And then if U cross V, the cross product, is 0, you're saying that those two vectors are parallel. So cross being 0 gives me parallel vectors, and U dot V gives you orthogonal vectors. Nice. Very cool. Yeah. Now they don't say this U and V are parallel because this assumes that U and V have to be non-zero. So saying it this way allows U and V to be 0 and it's still correct, right? Saying it's parallel, you're putting in a little extra baggage, assuming that U and V are non-zero. But this is true if one of these was 0 nonetheless, yeah? And so they would still be scalar multiples of one another, okay? Awesome. Now, let's get to maybe a final geometric thing that we can say here about the cross product, or at least the magnitude of it. And this is kind of a neat little math geeky application of this that comes up from time to time, so it's kind of a nice thing to know. And it starts off with the following. Let's go ahead and I'm going to throw down a vector U, and then I'm going to throw down a vector V, something like that. And theta would be the angle between them then, like this, right? And if I was to draw a certain shape here, for instance, what if I made a copy of V over here and made a copy of U over here, like this? I would make a parallelogram, right? Right? So I would have this parallelogram here, right? Now, because the cross product has something to do with sine of theta, it might be interesting to think of this right triangle here. In other words, what is the height of this triangle, and ultimately, what is the height of this parallelogram? Well, it is the opposite side of this right triangle here. And so that involves the sine function, right? So sine of theta equals the height of the parallelogram over the magnitude of the hypotenuse. which is going to be magnitude of v. So the height, h, is actually equal to the magnitude of v times sine of theta. Now, what would be the area of this parallelogram? The area of a parallelogram is simply the length of its base times its height. So let me go ahead and write that down. The area of the parallelogram is its base length times its height. Right? Well, the length of its base, that's however long u is, right? So that's going to be magnitude of u times the height. The height we just figured out was the magnitude of v sine of theta. And there's our little formula. Look at that. Magnitude of u times the magnitude of v times the sine of theta, which is literally the magnitude of the cross product. So another way to think about the magnitude of the cross product is that it forms the area. It's the area of the vectors of the parallelogram whose vectors form the sides of that parallelogram. Right? So the area is the magnitude of that cross product. Okay, so that's rather nerdy. I like that. that's a rather geometric idea there, right? And so for magnitude of u cross v equals the area of parallelogram. Parallelogram having u and v as sides. Yeah, I guess as adjacent sides, I should say, to be very correct. Adjacent sides. Okay. All right. So those are some geometric things that are going on there, right? Now, other things that we can do with this, right? For instance, what if I took I, the vector I, and I crossed it with j, right? Right, what if I took I and I crossed it with j? Well, I could certainly do this calculation, right? It's not going to be too hard, and I can certainly do it that way. But I wonder if you could actually puzzle this out, thinking about the geometry of the situation here, right? And so I cross j. First off, those are both unit length vectors, right? And I know that it's got to be orthogonal to both I and j. So here is I and here is j, right? Forming the corner of the, here's the origin right there, and here's the 90-degree angle there. So I know that the cross product has to be pointing either straight up or straight down. In other words, it has to be parallel to k. It has to be parallel to k at least, right? Now, its magnitude has to also be the sine of the angle between these, right? And so the sine of the angle between these, right, is, this is 90 degrees, right? And so what is that going to be? The sine of 90 is 1, So the magnitude of the cross of I and j has to also be 1. It ends up that this is exactly equal to k. When you cross I and j, you get k. And this is called a right-handed system when you form this way. And so what you can do is take your right hand, right? Now, this might be mirrored on the video, I'm not sure. But this is my right hand, yeah? And you point your palm in the direction of I, you curl j towards j, and your thumb points in the direction of I cross j, which happens to be in the k direction, positive k. That would be a right-handed system. In a left-handed system, I would point towards I, and I can't naturally curl towards j because j is actually the other way. So I would have to take my same right hand and I'd have to rotate it. Then I can rotate towards j naturally, and now k is pointing downwards, right? So the positive direction is that way, yeah? This is how you can figure out what direction that the cross product is going. We follow a right-handed system. So you can always point your palm in the direction of the first vector, curl it towards the second vector, and wherever your thumb's pointing, That's the direction that the cross product is going to be in. Yeah. And so that's a nice sort of everyday sort of thinking and geometry of what direction does that cross product go. Because when I say it's just orthogonal to two vectors, it seems like there's many choices, right? I could have definitely, if it was on the corner, it could be pointing up or pointing down. Which one is it? Well, it follows the right hand rule. And so that is something that we can get to. Yeah, very cool. All right, let's apply all this that we've learned here and get to some example homework problems. Yeah, let's do it. So first things first, we are being requested to find a unit vector. Find a unit vector that's orthogonal to both u, which equals I minus 4j plus k, and v, which is equal to 2i plus 3j. Okay? So we're tasked with finding a unit vector that is orthogonal to both of these vectors. Well, first things first, I don't know if I can find a unit vector directly, but I can certainly use a tool called the cross product to get you orthogonality. Then, once I have that vector, I can adjust it so it's unit length. You see that? So I'm going to get the vector pointing in the right direction first, and then scale it so it's unit length. So the first plan of attack here, let's take the cross product of these two vectors. This will guarantee the orthogonality. 1, -4, 1, 2, 3, 0. Okay. So let's go ahead and do this. I, 0 minus 3 minus j. J is going to be 0 minus 2 plus k, 3 minus minus 8. 3 minus minus 8. So you get negative 3i plus 2j. 3 minus 8, so 3 plus 8, which is 11, plus 11k. All right. Now, what I know is that's orthogonal to both of these, but I'm pretty sure it's not unit length, right? So now I am going to find a unit vector in the direction of the cross product. So now to do that, all I have to do is take that cross product and divide by its magnitude, right? That will get me a unit length pointing in the direction of the cross product. And so I want to go ahead over here and let's calculate the magnitude. Now, if this was a physics problem, it might be better to use the magnitude of u times magnitude of v times sine of the angle between them. But do you notice I don't know the angle between these? So I better just take the magnitude of this vector. I already have it in component form. And so this is the easiest way here, in this case, to find the magnitude. So I'm going to say this is a square root of 9 plus 4 plus 11 squared. I think that's 121. And so I get 125, 134, square root of 134. Okay. Which means that if I want to have this unit vector, all I have to do is multiply u cross v by 1 over this. And so my final answer here is going to be the following. Negative 3 over root 134, I, plus 2 over root 134, j, plus 11 over root 134, k. That is a unit vector orthogonal to both u and v. Notice that there's actually two answers to this, right? Because there's one that could go, this way, up, and there's another one that can go this way. So we chose the u cross v, but it could have just been done with v cross u, and in fact, the exact opposite of this is also a correct answer, right? Because that is a unit vector orthogonal to both of these as well. So there's actually two legitimate answers here. right? Now you can't take any multiple of this because it said unit vector, but there are two unit vectors, one pointing up, one pointing down, up and down in quotes, that make that true. So there's actually two answers. Okay. All right, let's see what else we got here. Okay. Yeah, so here's a little geometry problem. They're going to give you the vertices of a quadrilateral. Okay. So we have A, which is 5, 2, 0. We have B, which is 2, 6, 1. We have C, which is 2, 4, 7. And we have D, 5, 0, 6. Okay. Now this forms a quadrilateral. They say show that it's a parallelogram. So remember, a quadrilateral just means four-sided figure. You don't know anything about the sides except there's just four of them. But they're claiming that this forms a parallelogram, and then they want us to find the area. So show this is a parallelogram. And find its area. Okay, I think I'm going to use GeoGebra to at least visualize what's going on here. So let's go ahead and do this. Get the 3D graphics going here. And I'm going to plug in these points. A equals 5, 2, 0. So there we have A. B equals 2, 6, 1. C equals 2, 4, 7. And D equals 5, 0, 6. And to make this a little fancier, I think I can actually use, yes, I can use a polygon tool. I can click on this here, polygon, and then just start at A, click on A, then click on B, then click on C, then click on D, and then click on A again, and boom. There we have it. That is what we're working with, right? Very cool, all right? Well, it kind of looks like a parallelogram. You know, that's not a proof though, right? It looks about right. That's for sure. It looks about right. In fact, I could even do something like that. Look at that. Yeah. So what is a way that I could actually prove that this is a parallelogram, right? And so one way I could do that is to think about the vectors formed, right? Think about the vectors formed here. So I could form vector, let's say AB, which is the one running along the bottom here, and then form vector DC, right? And see if those are multiples of one another. If they're a multiple of each other, then that means that this is parallel to that. Then I could take AD, vector AD, right? And take vector BC right here and show that they're parallel by showing that they are multiples of one another as well, right? So let's go ahead and do that. I'm going to form a few vectors, right? With this picture in mind, I'm going to form a few vectors. Let me write these down. I'm going to find AB, vector AB. I'm going to find vector DC. I'm going to find vector AD, and I'm going to find vector BC. Okay. Now let's go ahead and go to paper here. AB is going to be the vector 2 minus 5, so negative 3. 6 minus 2, which is 4. 1 minus 0, which is 1. So negative 3, 4, 1. DC, so starts D, ends at C, so 2 minus 5, negative 3. 4 minus 0 is 4. 7 minus 6 is 1. Right? Oh, and not only are they parallel, they're equal as vectors. By the way, that's what has to happen with a parallelogram, right? Not only are the opposite sides parallel, but they have to be congruent as well. You know? And so that's going to show up with a vector as being the same exact vector. The only difference would be that if I did CD, it would point the other way. Right? It would point the other way. but that would still be fine because the magnitude is still the same. And so AD would be 5 minus 5, so 0. 0 minus 2, 6 minus 0. BC, so ending here, 2 minus 2, 0. 4 minus 6 is negative 2. 7 minus 1 is 6. And indeed, these are equal, and these are equal. That shows it's a parallelogram, right? Opposite sides are not only parallel, but they're congruent. Okay, now we know we have a parallelogram, which means I now have to find the area of such a thing. And that is going to be quite useful for the magnitude of the cross product. Now, the cross product of what two vectors? Let's go back to GeoGebra here. I just need to pick any two adjacent sides. So I can pick vector AB, and I can pick vector AD. AB and AD would do the trick. So let's go ahead and take the cross product of those. So I'm going to say I have, I want to take AB, and I want to cross it with AD. And then I want to find its magnitude, and the magnitude of that cross product is the area of the parallelogram. So I'm going to first off find this, I, J, K. AB is negative 3, 4, 1. AD is 0, negative 2, 6. That. And so taking that cross product gets me 24 minus a minus 2. 24 plus 2 is 26. Minus J, so negative 18 minus nothing. Plus K. 6 minus 0. Get that. So it looks like I end up with a cross product of 26I plus 18J plus 6K. Now all that remains is to find the magnitude of that vector. So the magnitude of AB crossed with AD should equal the magnitude of this. So square root of 26 squared plus 18 squared plus 6 squared. Doing that in my calculator. Oh, I won't. Yes, I will. I was like, where's my calculator? Gets me what? 26 squared plus 18 squared plus 6 squared. Gets me 1036, the square root of that. And the square root of 1036 is 32.19. And so there we have the area of that parallelogram, 32.19 square units. Now that's actually quite a difficult problem because this parallelogram was not in a two-dimensional flat thing. It's embedded in a three-dimensional universe. So it's harder to work with, right? You're like, well, just take the base times the height. And you can, but how do you know what sort of angle the height is making, right? And so being that this is embedded in a three-dimensional space can make that a little bit tougher to work with just simple geometric tools. So it's kind of nice to have this cross product that doesn't care where it lives, right? That it's just, hey, tell me the two sides as vectors, take their cross product and find their magnitude, and that's going to be the area of that thing. By the way, do you notice GeoGebra over here? Look at this, 32.19. So when it drew this quadrilateral, it just automatically calculated the area. That's really nice to see. That's what we got, 32.19. Very cool. So we were able to find the area of that. Okay, now, let's see here. We have a couple more things that I want to talk about with cross product, but I think I'm going to leave it for now because we've done a lot today with other things. We still have torque to talk about. Torque is an application of cross product. And then we got something called the triple scalar product, which is useful in some mathematics as well. But that's it for 11.4. You got the core idea of that cross product. And so next time we'll finish off the cross product in 11.4, and then we'll move on to 11.5. Now 11.5 is a meaty section. A lot of stuff in it, a lot of stuff to chew on. as we try to grapple with lines and planes in 3 dimensions, right? So you know all about lines in 2 dimensions, y equals mx plus b. But to figure out a line in 3 space, it requires a little bit different of approach, right? Rise over run is no longer a thing that we can use because run is not specific enough, right? Which way do I run? Do I run that way, that way, that way? There's 360 degrees worth of directions I could run in, right? So run by itself is not applicable anymore, right? And so we want to figure out how can I describe points that live on a line, points that live on a plane, and of course the tool that we're going to use to do that is vectors. Yeah. And so we'll end up doing that on Tuesday next week. Looking forward to checking in with you then. Hope you all are taking care of yourself, taking care of each other, staying healthy as best you can. And until next time, everyone, I hope you stay well and be well. Bye now.
I